Chapter 5.2 Faraday's Law and Magnetic Flux. Let's begin. Turning a conductor into a power source. In the last chapter, you learned that a conductor cutting magnetic field lines may induce an EMF. In the figure, there is a conducting wire named electrodynamic tether, extended from the bottom of a satellite. This conductor wire cuts the magnetic field lines of the Earth as the satellite orbits the Earth. Hence, there is an induced EMF across the wire, which may drive a current and therefore generate electrical energy. In this chapter, we will further discuss Faraday's law. We will learn the mathematical form of Faraday's law and see how we may apply the law in different situations. 1. Magnetic flux and flux density. A. Magnetic flux. You should still remember the two different situations when an EMF is induced. One is when a conductor experiences the change in magnetic field, and the other is when a conductor cuts magnetic field lines. In both cases, we must first measure the number of field lines, which is called magnetic flux. Strictly speaking, magnetic flux measures the amount of magnetic field lines crossing an area perpendicularly. It has a symbol, represented by the Greek letter phi, and has a unit of Weber, WB. As the density of field lines is directly proportional to the strength of the field, a stronger magnet with a larger area should produce more magnetic field lines. So, magnetic flux phi equals magnetic field B multiplied with area of the pole face A. On the other hand, if a coil of area A experiences a uniform magnetic field B as shown in figure 5.2a, we may calculate the number of field lines, so-called magnetic flux, that passes through the area, again by the same formula, phi equals BA. In case the area and the field lines are not perpendicular, the component of the area or the component of the magnetic field perpendicular is first calculated. Hence, phi equals BA cosine theta. For the coil that has n turns, the total magnetic flux experienced by the coil is n phi that equals n BA cosine theta, which is called magnetic flux linkage, which is very important when we apply Faraday's law. B. Magnetic flux density. From equation 1, we may express magnetic field as phi equals A, so that magnetic field is the density of magnetic flux. In other words, magnetic flux density, which is a unit of Weber per meter square, or simply Tesla. Now, let's see how these equations and concepts are applied. Example 4. Calculation of flux and flux linkage. There is a pair of magnets of the same pole face size and strength. In between them, there are some magnetic field lines, and the amount of magnetic field lines is called magnetic flux, which is given by phi equals BA, the strength of magnetic field multiplied with the area of the pole face. So you may say there are 3.6 times 10 to the power negative 7 field lines direct from the north pole to the south pole, evenly distributed between the two pole faces. For part B, there's a coil, probably have the same size as the pole face, with all the magnetic field lines pass through the coil, and hence the magnetic flux linkage is N times phi, which is 7.2 times 10 to the power negative 5 Weber. Now, what if the coil is smaller in size? Say it is a circular coil of area 1 cm square. Then the magnetic flux linkage will be N times 5 again, which is NBA, and that will give 3.6 times 10 to the power negative 5 Weber only. 2. Mathematical representation of Faraday's law and Lenz's law. Now, Faraday's law can be restated mathematically. The induced EMF is equal to the rate of change of magnetic flux or the rate of flux cutting. To include Lenz's law, and for a coil with n turns, the equation is written as epsilon equals negative n multiplied with delta phi over delta t, which means the rate of change of magnetic flux multiplied with n. The equation appears complicated. There are 4 variables. They are n, b, a, theta. But usually only one variable changes with time, so we may rewrite it in 4 different forms. To begin with, we will apply the first equation in example and exam link that follows. And I will present the answer differently from your book, so that you may cross-check and understand better by comparing different presentations. Now copy down these equations.